In this video, I'm going to discuss momentum, which is discussed in your textbook in chapter 11. So I'm going to make some brief remarks in this video, and the details I'll let you read the textbook for that. So in a few words, momentum is the combination of mass times velocity. It's a product of those two. If we use a more scientific notation or more abstract notation, we'd use the letter m for mass and v for velocity, the vector velocity v. A standard choice of letter for momentum is the letter p, so we'd come up with p equals mv. A quick remark about the units. So as you know, velocity is in meters per second, mass is in kilograms, and so the combination of momentum which would be mass times velocity, is going to be in units of kilograms meters per second. And this stays like that. There's no particular name for this combination of units, and so we just refer to momentum in kilograms meters per second, or sometimes more simply we'll say units of momentum. So one of the things that's interesting about momentum is to consider the rate of change. And so if we are interested in that, we will start with the definition of momentum and write it this way, and then we will ask the question, how is this going to change over time? So we will be interested in the derivative of momentum with respect to time, so it'd be the derivative of this combination of terms, m times v. If we apply the product rule, then we would say this is going to be the derivative of the mass with respect to time times the velocity, plus the mass times the derivative of the velocity with respect to time. Now we are going to be interested here in cases where the mass will remain constant, and so we will consider that this to be equal to zero. It's not always true, but we are going to simplify our discussion here by focusing only on cases where the mass is constant. So what's left when we do this is that the rate of change of momentum, the dp over dt, is going to be equal to the mass times the derivative of the velocity with respect to time. And as we know, that's what we defined earlier in the course as acceleration. And then we see now that we have a combination of mass times acceleration, which we also recognize as the net force acting on an object. So this gives us a new formulation of Newton's second law, which says then that the rate of change of momentum is equal to the net force. And that's actually the way Newton himself discussed the whole problem. So if you want to change the momentum of an object, what you need to do is you need to apply an external force to it. So that's an important result here, and that's another way of describing Newton's second law. Now, what we're going to do is simplify the discussion by focusing on one-dimensional problems. So we will get rid of the vector notation, so only 1D problems are going to be our focus here. So we don't need to use the vector notation. So instead of writing p with a vector on top, I'm going to write simply p. But then we will use a plus if it's in the positive direction, and minus if it's in the negative direction, because if you look at the definition of momentum, p equals m times v, you realize that the velocity vector and the momentum vector have to be in the same direction. So those two will always have the same direction, and so whichever way the object is moving, that's the direction of the momentum. So on in a one-dimensional problem, when we only look at objects that are moving along a straight line, if we choose, let's say, a positive direction to be left to right, as we said earlier, an object moving to the right would have a velocity that will be positive, and so the momentum in this case would also be positive. Okay, so now we also say this is also going to be a positive value. Okay, so we'll get rid of the vector notation. We'll just use that as I said, we'll just use the p. Same thing for the velocities. We can drop the vector and then we'll use a v with a plus or minus. Okay, let's clean this up. And then without the vector notation. Okay, so now our previous equation is going to look like this. The rate of change of momentum equals m times the rate of change, times the force, since we want to go to the force expression instead of Massim's acceleration. We'll simply say then that the rate of change in momentum is equal to the net force applied on the object. Now, one of the things we are interested in is, therefore, how does momentum change when we apply force? So we are, as we said, we would write this. And so we can turn that around and say that a small amount of change in momentum, a small dp, is going to occur whenever we apply the net force for a short amount of time dt. So we simply cross multiply here. And we want to look at the overall change of momentum when the force is applied for a significant amount of time. So we're going to integrate on both sides of this equation. And if we integrate on the left-hand side and the right-hand side, we're going to get two different things. So on the left-hand side, we will get the integral of dp, which will turn into the momentum, but there would be between the final momentum, which is the end of the process, and the initial momentum. So this will give us a quantity which will be the difference between the final momentum and the initial momentum, and this is what will be referred to as impulse. And there is a notation that the textbook uses, which is to use a capital J for this, but specifically what it refers to is the difference between the final and the initial momentum, always in that order, final minus initial. On the right-hand side of that equation, we had the net force over time dt. So the integration here is between the initial time when we start applying the force and the final time when we stopped applying the force. So what we're getting now is that the impulse, so the j, if we use this notation here, is going to be equal to the integral of whatever the force is over the range of time during which we apply the force, that is from the initial to the final time. Now here we have multiple possible cases, okay? So we're going to look more carefully at the following cases. First, we're going to consider that the net force is varying, is a function of time, okay? So that means that the magnitude of the force is going to change, and possibly the direction as well. In a one-dimensional problem, that means the force can reverse direction. We'll look at examples of that. The second option would be that the net force is constant. So here we mean something other than zero. So constant but different from zero. And then finally we'll look at the third case, which is what happens when the net force is equal to zero. So what are we talking about then when we say the function of time? So this is the first case we're talking about. F net is a function of time. So here's a quick example. This is from a textbook on not a textbook, but actually a book on baseball. And in that book, you will find pictures representing the value of the force. And so here's an example of that. So I'm going to show you a picture representing the magnitude of the force. So maybe I should move that here a little bit here. And so as you can see here, we have different examples of hits. So this is a home run, short fly for this one, and a bunt for the third one. And the magnitude of the force is shown right here. This is in pounds, but it doesn't matter. It's the same idea. And then the time here, notice here, this is in milliseconds. So what happens is, let's take the home run as our example. The force was initial zero. That's between the bat. The force that we're talking about here is the force between the baseball and the bat. So before contact, the force is equal to 0. Then it increases and it reaches some sort of maximum value here. On this scale, it's pretty large. It's about 10,000 pounds or so. But it only lasts for a few milliseconds. In fact, it's not even a full millisecond, as you can see here. So the difference of time, the t final minus t initial, in this case, is about 1 millisecond. So a very short amount of time. So the question is, how do we handle this kind of thing? So what we were trying to do is we're trying to compute the impulse, the j, as the integral of over the force times dt, the net force. And so, as you recognize from calc, this means essentially finding the area under the curve. So if I bring up this picture again, where was it? Here. So what we're talking about is finding the area under this function. So since we focus on the home run, the function is right here. So all of this. And what we're trying to find is the area under the curve. So this would be represented by all of this particular part here. This is the area. So this area would actually represent the impulse applied by the, let's say, the bat on the ball. So if we could somehow find the amount of area, then we can figure out the impulse. The problem, of course, is that this may be complicated. So we would have a couple of ways to do this. So either we know a function of time, which would be an ideal thing. So if we have a function of time, then we could certainly apply calculus. So for instance, I won't do the detailed calculation here, but imagine that the force, the net force as a function of time is given like something like a maximum function, a maximum value times 1 minus e to the negative some kind of constant times t. So if you plot it, you'll see that this is a function that increases like this. It starts at 0 and eventually reaches some kind of maximum. So this would be an example where you'd have to integrate the function between, say, an initial time and a final time. And if you wanted to do that, then you would be looking for the area under this curve right there. And that would be the impulse given by the force during that time. That's one option. Another option would be that the force is given in a simpler version, or we can make some kind of approximation. So if we look at that force again, and we see that it is essentially symmetric, meaning it increases and decreases nicely like this, where the force is reaching a maximum value here. This would be the maximum force. And the time that we're interested in somewhere, let's say between here and here. So this is the initial time, and this is the final time. So here this is t. So technically we're supposed to be looking for this area. One thing we could do to simplify the problem is to replace this complicated function by an average value and assume that this is actually constant for this period of time. If we manage to find a way to get this area in green to be the same as the area in red, then the impulse will be the same, and this is much easier to figure out because in this case the area is just the area of a rectangle, which is much easier to work with. So it'd be nice if we could simplify this. There are some standard procedures which would say that we would find the average force, if it's very symmetric, by taking the maximum value of the force and divide that by 2. So if we could do that, that could be a simplification of the problem. Instead of having to deal with this complicated function, we could do this. Okay, so there will be examples in the book where this might be doable, but otherwise we would have to know some more about the function, the force, in order to be able to do this kind of calculation. Another option would be if the force is given in simple geometric terms. So for instance, if we have a force that's changing in time in a nice smooth fashion, let's say as a triangle, then in that case, it's pretty straightforward. What we need to do is find, as I said earlier, the area under the curve, which is here the area in the triangle. So if we know what this time is, we would simply multiply the base times the height. So the area would be the area of a triangle. So we would multiply the base times the height and divide that by 2. And that would be the impulse. So let's run through a quick numerical example just to solidify those notions. So suppose, for instance, that we have a case where the time here is 3 seconds, and the peak value here is 12. No, let's make it 8 newtons. So let's assume this is 8 newtons. And we ask for the impulse. So the impulse in this case, J, would be 3 seconds, that's the base, multiplied by 8 newtons, that's the maximum value, divide that by 2, and we end up with 12. An interesting thing to note here is that when it comes to the unit, we could keep the units the way they are, and so we would have newtons multiplied by seconds. And if you work out the details, you'll see that this is exactly the same thing as kilogram meter per second. So in fact, when it comes to the units of momentum or impulse, we could keep that either in kilogram meters per second or convert that into Newton seconds. This is Newton's times seconds, which will be sometimes convenient as a unit for momentum. What if the force is different? So earlier I've been talking about the varying force. Let's take a case where the force is actually constant over time. So let me go over this for a second here. So this is the second case. So if we have a constant force, then the problem is much easier to handle. So by constant force, what I mean is a situation where the force would be applied for maybe a short period of time, but during that time, the value of the force is constant. So we'd have this force here, this would be the maximum, and the amount of time that we apply the force over is just this much. So in this case, this is the initial time, this is the final time. So if we go back to the calculation of the impulse, the J, we had earlier the integral of the net force over the time range, but if the net force is constant, then we can take it out of the integration sign, and we can say that the impulse is the net, whatever the net force is, integrated times the integral of dt between the initial and the final time. But that is the following. So the J is going to be the integral of the integral of f times the integral of the force of the time. So you would get this. So the net force times the integral of dt between the initial and final time, which gives us the net force times t final minus t initial. And this we can refer to as delta t, as we've done it many times. So we can say that the impulse, which is itself the change in momentum, is equal to whatever the net force is multiplied by delta t. So going back to the picture I was showing earlier, the force is constant when it's applied or while it's applied. This will be, if this is t and this is a force, so the value of the force is whatever this thing is. And then the delta t is right here. So we would simply multiply base times height. That's essentially finding the area of this rectangle here. And that's what the impulse would be. So one of the things we could do with this kind of thing is, for instance, remembering that delta p stands for the final momentum minus the initial momentum. And the right-hand side being the net force times delta t, where delta t is the amount of time the force was applied for. Then we can solve, for instance, for the final momentum by adding to the initial momentum whatever the net force is, multiplied by delta t. So let's try to use this in example. So let's consider the following. Suppose we have let's actually do it here, a different page. So imagine we have a box sliding on a flat surface, and the box is initially moving to the right with an initial velocity equal to, say, 6 meters per second. And we'll assume the mass of the box is 2 kilograms. And this is sliding on a surface that has no friction. And then suddenly it reaches a point where there is like a rough patch. And so suppose that from here to here there is friction. So we have friction to worry about over this range. And the box is going to go across this area, this length here, in a time, delta t, that let's say is 0.5 seconds. And so the question is going to be the following. What is the velocity of the box after it goes over the patch and goes back to a surface where there's no friction? So that's the question. What is the final velocity here? So applying what I just talked about, we would say that the final momentum is going to be equal to whatever the initial momentum was, plus the force, the net force, multiplied by delta t. So we need to know something else here. We need to know something about this force. So let's say we are given the following information, that the force in question, which obviously here has to be a friction force, is going to be oriented this way. It's going to be applied in this direction, and we will consider that it has a value equal to, in this case, let's consider 3 newtons, but since it's pointing to the left, we're going to write this as negative 3 newtons. So how do we figure out the final velocity here? Well, we will put things together and say that the initial momentum, before we go any further, the initial momentum was the mass times the initial velocity. So this was 2 kilograms multiplied by a velocity of 6 meters per second. So we had an initial momentum of 12 Newton seconds, or 12 kilogram meters per second. The force, the net force times delta t. So this was negative 3 newtons for the force, multiplied by 0.5 seconds for the amount of time. And so this gives us negative 1.5 Newton seconds. And so the final momentum is going to be the initial momentum, 12, plus the combination, or plus the F net times delta t, which is negative 1.5, and that gives us, should be 10.5 Newton second. That's the final momentum. But the question was about the final velocity, so the final velocity is going to be the final momentum divided by the mass of the box, so it'd be 10.5 over 2, which gives us 5.25 meters per second. And so what happened here is that the velocity went down from before the box hit that rough patch, its velocity was 6 meters per second, and then half a second later it has changed because it has reached this particular patch here where there is friction, and then the box goes on and picks up a different velocity, which will be a final velocity of 5.25 meters per second. So that's how you would use this kind of calculation of the impulse to answer this kind of question. All right, so now we get to the third part, which is what happens when the net force is equal to 0. So from what we wrote earlier, so the change in momentum, the impulse, the j, would now be equal to the integral of f dt, but if the net force is 0, then there's nothing to worry about on the right-hand side. This is just going to be equal to 0. What that means is that the final momentum minus initial momentum would be equal to 0, But if we are focusing on a single particle, which is a case where the mass doesn't change, then there's not much to say here except that the mass times the final velocity is equal to mass times the initial velocity, which tells us essentially that the final velocity is the same as the initial velocity. So we are basically looking at Newton's first law, just in disguise. It's the same situation. We did not apply any external force, so we don't expect the velocity to change. So in itself, this is not a very interesting example or problem. A more interesting situation would be one where we have a system that is made of multiple pieces. So this is an interesting case where we have at least, and we're going to focus on this example here, a system that has two objects, and specifically two balls or two blocks, depending on how we want to look at it. And so here we would have, for instance, two boxes that are, or two blocks that are initially together, and for one reason or another, we'll talk about examples in a second, they initially may have, let's say, an initial velocity that's equal to 0, and then at some time later, something pushes them apart, an internal process pushes them apart, and each box is going to move away from the other. And so this will be an example of what we will refer to as explosions, where the two things were initially together and then they get pushed apart. So that's the first case. Okay, so this will be one kind of example we'll discuss in detail. The second possibility would be one where those two boxes, instead of being together initially, are going to move, let's say, towards each other. So suppose, for instance, that they have, let's say, this is number 1 and this is number 2. They have a velocity, let's call it v1 initial, and this one would have a velocity in the opposite direction. So they are moving towards each other, but we want to think of the system as being the combination of these two things. And so this is what the system is going to look like. And again, here we would have a total momentum for the system. And we will say, because there is no external force, that the total momentum of the system is going to be equal to the total momentum so the momentum after collision is going to be equal to the momentum that we had before collision. And so this will be an example of what we will refer to as collisions. And we will look at more details of that in a second.